So good afternoon, everybody. This is ancient light. It's about imaging a quasar, catching the light from a quasar that's been travelling for billions of years, but without using a telescope. So this started as a lockdown challenge because in 2020 certain things happened which you probably remember. This object gave rise to a lot of other objects on floors of supermarkets and pavements all over the place. But I remembered the words of Stephen Hawking. Remember to look up at the stars and not down at your feet when you're trying to keep 2 meters away from everybody else. Try to make sense of what you see and wonder about what makes the universe exist. So I thought, if we need to remember to look up, how far can we see if we choose to look up? And that's what gave rise to the challenge. The universe, we all know, is vast and ancient, and large telescopes have imaged galaxies that are billions of light years distant. So the question I set myself was, is it possible to capture the light from one of these very remote objects, but without using a telescope? Spoiler alert, yes it is, otherwise I wouldn't be giving you this talk. So it started by reading an article in which a survey was done of lots of quasars. A quasar is the nucleus of a galaxy that emits so much light that it can be seen from enormous distances, many billions of light years. And a survey of these quasars was carried out in the years leading up to this publication in 2019. Now, we don't necessarily know what these quasars look like because they're too remote, but we think that if we got close to one, it might look a little bit like this artist's impression. Almost certainly, to account for all the energy that's coming out of a quasar, there has to be a supermassive black hole at the heart of the galaxy that forms the quasar, and matter is falling into that supermassive black hole, and that's producing the enormous energy output. So, of this survey, I selected one of the quasars that was suitable for viewing from the United Kingdom. I picked one that was high in the sky during the summer of 2020. It goes by the name of J161737. It hasn't got a very pretty name, it's just named according to its position in the sky. And this is the spectrum that was produced in this survey. The spectrum showing the intensity of light from the blue end of the spectrum to the red end of the spectrum. And it doesn't look very interesting, except for the fact that there is one feature in there which can be identified as, in the laboratory, this feature would be visible at a wavelength of 1200 angstroms, or 120 nanometers, angstrom being 10 to the minus 10 meters. So this particular wavelength for a static laboratory source would be visible at 1200 angstroms. But in this particular spectrum, it's visible at 6500 angstroms. It's been shifted all the way from the ultraviolet into the red end of the spectrum. It's had a huge redshift. We can quantify that redshift by taking the two numbers where we observe it, 6500, and where it would be if the object wasn't moving, 1200. We can take the difference of those two numbers and divide by the smallest of the two. And then we get the redshift, which is 4.3. And a redshift of 4.3 means that this object must be very remote. It's very remote, and in an expanding universe, it's receding from us very quickly, at very high speeds. And that's what gives rise to the stretching of the wavelength that's taken a very small wavelength in the ultraviolet part of the spectrum and has stretched it out from 1200 to 6500. It's the expansion of the universe that has stretched the light from the ultraviolet to the red. And quantifying the redshift as 4.3 gives us a very remote distance. And I'll be talking about how we calculate the distance in a little while. So how did I capture the light from this quasar? I used my Nikon DSLR camera with a 300mm lens, and I put it on top of a star tracker, this Iopton star tracker. Other star trackers are available. The star tracker is just the white box there. It's effectively just a motor in a box. and it turns the camera at 1 revolution a day. So as long as you plonk it down correctly and align it with the Earth's axis, as the Earth rotates and the sky appears to move, the camera should track the sky and allow you to take long exposure images. The camera and lens that I'm talking about here are not in any way adapted for astrophotography. They are the same camera and the same lens that I use, for instance, for wildlife photography. I've got an interest in going on safari and taking pictures of animals. So this camera equipment has not been customized, it's not been modified for astrophotography. It is the same camera and lens that I have used in the past to take pictures, for instance, of zebra. And the question is, if this camera is perfectly good at taking pictures of zebra in sunlight, is it any good at capturing the photons of light from a quasar that have been travelling for billions of years? So, the quasar itself is located in the constellation of Draco. I looked up its coordinates and determined that it was at that position. The rectangle there shows the field of view that I can expect from a 300mm lens on my camera. You can see it's in the middle of the constellation of Draco. On the right hand side there is the constellation of Ursa Minor, with of course Polaris on the extreme right of this image. The dot you can see right in the middle of that rectangle is not the quasar is much fainter than that. It just so happens that the quasar, by line of sight, happens to be close to a star which we can actually see. That star is called AT Draco, and I could see that through the viewfinder, so by centering that through the camera I knew that the quasar was very close by. So I focused on that star and then focused on a slightly fainter star, about 8th magnitude or so, in order to make sure the camera was perfectly focused. I then took the longest exposure I could. This was taken during July of 2020, so during the summer months in the UK, as you're all aware, we don't have a particularly long night. I figured I could expose for about 2 hours, about an hour and a bit either side of midnight, either side of 1 o'clock in the morning BST. And I didn't want to take one long exposure, I took a series of short exposures. I took over 100 short exposures. As it happens, there was some cloud coming over, so having taken a lot of short exposures, afterwards I looked over them, realised that some of them had clouds passing and so threw those away, and of the remaining images I added them all together to get the equivalent of a 2-hour long exposure. And there we can see the bright star AT Draco in the centre, and I figured that the quasar ought to be in that square just next door to AT Draco. So having got my final image of the equivalent of 2 hours exposure, I blew up that particular part of the image to see what was there. And right at the middle of that particular crop of the image, there we have the quasar. So yes, it is possible to catch the image of a quasar even using a telephoto lens rather than a telescope. Most of the light from the quasar is focused into just 1 pixel in the image. If we blow up what's at the centre of the screen there and just brighten slightly some of the surrounding pixels, just so you can get a bit of an impression of what's going on there, you can see that most of the light has been focused into just 1 pixel out of the 20 million pixels of the image. It's a 20 megapixel camera, so I had 20 million pixels in the final image, but most of the light from the quasar has gone into just 1 of those pixels. Just as an aside, what sort of resolution might we expect from the lens and the camera? I did a quick calculation just to check. With a 300mm lens, which is f4, meaning that the aperture of the lens is 1/4 of the 300mm focal length, if you like, that's equivalent to a 75mm aperture, then that ought to produce images with a resolution of about 9 microradians, 9 millionths of a radian, or a little less than 2 arc seconds. That's assuming that the lens has no imperfections and that the resolution that I can expect is that of a perfect lens. Okay, the lens is not perfect, but I paid a few £100 for that lens, so I expect it to be good, and I don't expect the lens aberrations to stop me achieving that level of resolution. If we look at how big the pixels are in the camera, with a 300mm lens, the pixel separation, or the pixel pitch, if you like, is about 15 microradians, or about 3 arc seconds. In other words, it's reasonably closely matched. The limit of resolution of the lens is very close to the actual pixel pitch of the camera. And just to put it in perspective, if we take an object like the Milky Way with a diameter of some 150,000 light years, if we take that object and move it a few billion light years away, it would subtend an angle of order perhaps 30 microradians, or about 6 arc seconds. So in other words, if we were to place the Milky Way many billions of light years away, it would be imaged as only a couple of pixels in this particular setup of camera and lens. Just as an aside, when I looked at this particular crop, which is only 8 arc minutes by 8 arc minutes in size, compared to the total image, which is about 3 degrees by 2 degrees, I had a look at the various objects I could see there, apart from the quasar that's at dead centre there. And I realised that the stars come out as nice circles, but some of these objects are quite elongated. And I checked this against the star atlas and found that some of the objects that were imaged in this crop are not stars, but are galaxies. So most of the objects you can see in that picture are stars in our Milky Way. A few of those objects are more remote galaxies, and the central object is the quasar itself. I don't expect you to be able to tell necessarily the difference between stars and galaxies in this image. I simply had to check it against a reference plate to find out which were stars and which were galaxies. But if there were 10 galaxies in that very small crop of the image, and assuming there's nothing special about that particular patch of sky compared to anywhere else in the image, that means that the original 3 degrees by 2 degrees of the image that I took probably captured about 7,000 galaxies in total. That's interesting in itself, I thought, not least because that's similar, it's comparable to the number of galaxies that were caught by the Hubble when it carried out the Hubble Deep Field images of many years ago. So let's come back to the elephant in the room. What is the distance to this quasar? I've claimed that it's a very remote object, but what is the distance to this object, the light of which I've caught with the camera? Well, we can think of the light leaving the galaxy on its way to Earth, and if we wish, we can say, well, that's what we can call the distance to the object, or at least it was the distance when the light left the galaxy or the quasar. But of course, it's taken a long time for that light to reach us. The light has taken billions of years to travel from the galaxy to Earth, and during that time, the universe has continued to expand, which means whilst the light is on its way to us, the galaxy is getting further away from us because of the expansion of the universe. And by the time the light actually arrives at Earth, the galaxy is further still away from us. So you can ask, well, which is the correct distance to the quasar? Is it the distance when the light left? Is it the distance when the light arrived? Or is it the distance that the light has actually travelled on its way from the galaxy to Earth? So you could argue that all of those 3 distances are correct. You just have to be careful as to which one you're using. And some people can be a little bit slapdash about talking about distance without making it clear which distance they're talking about. But it's not made easy by the fact that if we ask the question, how far has the light travelled? Well, that in itself is a rather tricky thing to answer, because as the light is travelling on its way from the quasar, from the galaxy, to Earth, it's travelling through space, and space is continuing to expand as the light is travelling through it. It's not simply that space forgot to expand after the galaxy has left and the galaxy continues to move away. Space itself is expanding, so all of the distance from the galaxy to Earth is changing as the light travels through it. It's a bit like an analogy saying, let's imagine a swimmer swimming through water. A swimmer swimming through a swimming pool water, you can tell how far they've travelled in a given time. But what if they're travelling through water which is moving? What if they're travelling through a water and they're swimming against the tide? Then working out how far the swimmer has actually swum is more tricky. Another analogy would be, think about an ant walking along a rubber band. If the rubber band is static, you can watch the ant move along the rubber band and you can see how far the ant has travelled in a given time. But what if, during the ant moving along the rubber band, somebody is stretching the rubber band backwards? Then asking the question, how far has the ant walked, is a more tricky question. It depends on how fast the ant was moving relative to the rubber band and who is stretching the rubber band and how quickly. So it's a tricky thing to answer. And the only way we can actually answer that question in terms of light travelling from a distant object to us is to have some idea of how space is expanding, how the universe is expanding, and most importantly, how it has been expanding ever since the light left the galaxy. We have to have some idea of what the universe has been doing for all of the billions of years that the light has been travelling from the object to us. And we do have a rough idea of what the universe has been doing. There's various ways we can access that information. I'm not going to go into the details, but we now have an idea of how the universe has been expanding since the Big Bang some 13.8 billion years ago. We've got an idea of how it's been expanding and the expansion rate and how that has changed with time. And using that information, we can work out the distance to objects for any given redshift. Remember, redshift is a consequence of the expansion of the universe, and it's the observable, it's the thing that we can actually measure, how the spectrum of an object has changed. And here we've got three lines. The blue line is the distance to the object when the light left. The green line is how far the light has travelled, and the red line tells us how far that object is away now that the light has arrived. And you can see the red line is getting larger and larger and larger as time goes by. It looks a little odd that the blue line is coming down again. Why should the blue line go up and then start decreasing? Well, because we're looking back in time. For objects that are billions of light years away, we're looking at them as they were billions of years ago. And billions of years ago, the universe used to be smaller because the universe is expanding. So we have this rather odd situation that if we ask how far away was the object when the light left, if we go back a long way in time, we find that the universe was much smaller. And so this blue line actually comes down for redshifts bigger than about 1.5. But let's look at this quasar. Let's put in the numbers for this particular quasar at a redshift we found earlier of z equals 4.3. Let's read off the numbers for that particular quasar and let's just erase the other lines because they're no longer important. So let's remind ourselves what these numbers mean. The quasar was about 5 billion light years away when the light was emitted. And how long has the light taken to reach us? The light from the quasar has been travelling for some 12.4 billion years. That is a huge length of time, remembering that the age of the universe is only 13.8 billion years. In other words, the light from this quasar has been travelling for 90% of the age of the universe. That's a phenomenal time. If we wanted to look back further than 12.4 billion years, well, we can do that. For instance, the Hubble Space Telescope can look back to about 13 billion years. My camera can go back 12.4, Hubble can do 13. You have to pay an awful lot for that little increase in look back time, that little increase in how far back in time can you go. During those 12.4 billion years, the universe continued to expand. So whilst the light was travelling, the universe continues to expand, and so the quasar gets carried along by the expanding universe, and the quasar must be now about 25 billion light years away. So we have those three numbers. It started at 5, now it's at about 25 billion light years, and it took about 12 billion years for the light to reach us. But some very simple maths tells you that something interesting is happening. The distance to the quasar has increased from 5 to 25 over a time period of about 12. The difference in these two numbers, 5 to 25, is about 20 billion light years. But it's travelled that distance in a time of 12 billion years. So, by simple maths, we can say that during those 12 billion years, the distance to the quasar has increased by more than 12 billion light years. Average speed is just distance over time. 20 over 12 is a number bigger than 1. It's about 1.6, which means the quasar, on average, has been receding from us. Its distance to the quasar has been increasing at the rate that is faster than the speed of light, more than 1.5 times the speed of light. Given that we know how the universe has been expanding with time, or at least we've got a good idea, we've got a good model that tells us how the universe has been expanding up till now, we can actually work out what's been happening to the speed of that quasar. And it turns out, when the light left that quasar to produce the image that we saw earlier, it was receding from us at more than twice the speed of light. And it started slowing down. Now, slowing down is not that unusual. If we've got a universe which is expanding, we would expect gravity to be slowing down that expansion. Gravity is always trying to pull everything together, so if all the objects in the universe are moving away from each other, we would expect gravity to be slowing down that expansion. And that's indeed what happened for billions of years. But notice what happens after about some 7 billion years after the Big Bang. It started coming up again. So after initially slowing down, the quasar is now accelerating away from us. Its slowest speed relative to us was about 1.5 times the speed of light, but it's now risen to some 1.7 times the speed of light and is continuing to accelerate. We don't understand why we're giving this acceleration a name. We call it dark energy because that sounds really cool, but we don't actually understand what dark energy is and why the universe is behaving this way. But it appears that that is what is happening. For billions of years, the expansion of the universe was slowing, but now the expansion of the universe is accelerating. If we think about what the light has been doing, here we've got a diagram, a graph if you like, of distance from us on the horizontal axis and time since the Big Bang going vertically. So distance from us is 0, that's where we are here and now. We are now 13.8 billion years after the Big Bang, so that's us now. And this is the quasar when the light left. The quasar was some 4 and a bit billion light years from us, and the light left. Remember, we're talking 90% of the age of the universe back. We're talking about when the quasar, something like 1.5 billion years after the Big Bang, the quasar emitted the light that we've just caught. So what happened to the light that left the quasar? Well, we might expect it to be heading towards us here and now. We might expect the light to get closer and closer and closer and closer to us as time goes by. So we might expect the light to do that. But no, the light is travelling through space, and space is expanding faster than the speed of light. So what is the light trying to do? The light is trying to reach us, but it's moving through space, which is dragging it backwards. So with a quasar moving at twice the speed of light, it means initially the light is actually getting further away from us. Even though the light is trying to get to us, because of the expansion of the universe, the light is getting dragged backwards. And for the first few billion years, the light is actually getting further away from us, until a point where it can just start to make headway, and then the light actually starts getting closer and closer and closer to us. So the light doesn't take a straight line on this distance and time graph because of the expansion of the universe. It's very non-intuitive because we don't tend to think about living in a situation where the goalposts are continuously moving. We tend to think of living in a world in which space and time are dictated by what we can see around us, not moving, and our watches. But the universe doesn't behave that way. So the light takes this rather odd route to get from the quasar to us. Whilst the light was taking that route, what was the quasar doing? Well, the quasar was getting further and further and further and further away from us, whilst the light was trying to make its way towards us. So the quasar was getting further and further away as time goes by, until it ended up some, I don't know, 25 billion light years away from us now. I've shown that as a dotted line simply because, remember what I showed a moment ago, the velocity, the recession velocity of the quasar is changing from 2.2 to 1.5 to 1.7 times the speed of light. So if the velocity is changing, that line shouldn't really be a straight line. It should be a slight wiggle because the velocity of the quasar is changing with time. And I couldn't work out what that wiggle should look like, so I've just drawn it as an indication of what the quasar is doing. The light is heading towards us eventually after getting dragged backwards by the expansion of the universe, and the quasar is getting further and further and further away from us. If we think about it from the view of the light, well, the light was emitted by the quasar 1.4 billion years after the Big Bang, 12.4 billion years ago. It had already been travelling for some 8 billion years even before the Sun and the Earth existed. It continued on its journey even when the Earth was born. It continued on for another 4.5 billion years. Life evolved on Earth. The light travelled on. Dinosaurs came and went. The light travelled on. In the last million years or so of its journey, the light arrived at the edge of the Milky Way, crossed a couple of spiral arms, and entered the solar system. In the last few hours of its journey, it arrived at Earth, travelled through the atmosphere in a fraction of a second, hurtled towards England, dodged a few clouds, entered the lens, and hit the camera sensor. Just a pixel in the image. But what a journey. So this is a graphical summary of what I've been talking about. The camera and telephoto lens in the bottom left were put onto a star tracker so that over a period of a couple of hours I could track the sky. The top left shows you where I pointed the camera. The rectangle shows you the field of view in the constellation of Draco. The main pane is the image that I ended up with, and the very central portion is cropped in the top right inset, which shows you the position of the quasar. So yes, without using a telescope, it is possible to catch what I like to think of as the quasar's ancient light. Thank you all for listening.